Okay.
Go ahead.
So, hi everyone, my name is Ariane Trudeau. I'm a PhD candidate at University of Victoria. And I'm going to talk about an exceptional mature galaxy cluster at a redshift of 2. But first, the motivation of that work. As Alicia mentioned in her talk, if you look at the local cluster, you're going to see a population of red and dead galaxies. But trying to understand for how long they've been passive is a bit tricky, because if they could be passive for like 10 or 12 gigayears, we don't know exactly. And doing this test with the SED modeling is difficult. If you want to convince yourself about that, think about the kind of stars that are going to move off the main sequence around 10 gigayears. If you cannot do this at low redshift, then you can go at high redshift and try to skip the gigayears of passive evolution. This way you can try to find a progenitor of this passive population when there was action. And even if you miss the time when there was action, you can still do a better SED filling, because there is more change between, say, 1 gigayear and 3 gigayears old SED than between 10 and 12. Finally, you can try to make links between the star formation history and the cluster assembly. This brings me to XLSSC122. I'm going to take a slightly different direction from other talks earlier today, and I'm going to focus on this object. Now, for some of you, XLSSC122 might be a familiar name. It was a subject of John Willis' talk on Monday. And indeed, here I'm just going to give you the highlight. And if you want to know anything more about the general property of that cluster, I advise you to go back and see John Willis' talk. So it is a cluster. It's X-ray selected. And here on the right-hand side of my slide, I'm showing you a three-color image of the cluster with the member highlighted and the X-ray contour in purple. We have also an SZ decrement measurement, and we have a descent mass estimate. It's at a redshift of 1.98, and we have 37 spectroscopically confirmed members. We have also 2 Hubble bands of observation for this cluster. And if you compare the two, you see that the cluster has a strongly bimodal population. But that's too bad, and there is more ancillary that are available for that cluster. So my goal will be to use this ancillary data to better characterize XLSSC122 galaxy population and to make link with the cluster assembly history. First thing first, photometry. I have 12 bands covering the near UV to the mid-infrared, and I use extractor 2.5.0 to extract the sources. I use image resampling, mostly because it's allowing me to do force photometry, which is very useful to deal with low signal to noise. And it's also very useful if you want to match one cluster member across several bands. The last thing I do is I compute an aperture correction factor to correct for the variation in the PSF. And here I'm showing you a MOFAT profile. I'm going to use that to do my aperture correction factor. A MOFAT profile is slightly different from a Gaussian profile. I can adjust the width as well, but I can adjust also the relative importance of the side wing. So it's very interesting to do this kind of calculation. What I do is if I'm interested in, say, the Z band, I'm going to choose a MOFAT kernel in such a way that when I convolve with my deepest F140 image, I'm going to end up with the same growth curve as in my Z band. For those of you who are not familiar with image processing and detector characterization, basically what I'm doing is I'm generating a convolved image, I will have the same resolution as, say, my Z-band. And now if I want to assess the difference between my Hubble image and my Z-band, PSF, and the impact on the flux, I can just compare the original F140 and the convolved one. So that's how I'm computing my aperture correction factor. Next step, do the fitting proper. I use BAGPIPES 0.8.4, which relies itself on multi-nest as state-of-the-art Bayesian fitting code. My fit are assuming an exponentially decreasing star forming rate, and they have 5 parameters: the mass, the metallicity, the dust content following a Calzadi extension curve, and the 2 parameters of interest for us today would be the characteristic time and the age. What I find is that this bimodal population is in fact a lot more diverse. Here I'm showing you the main type of galaxy I'm having. I divided them into 4 categories based on the age and on the characteristic time. And I advise you to note the color because I'm going to use the same color scheme throughout the rest of the presentation. One last note, you might notice that some galaxies are circled in brown, and those are the galaxies for which the data I have aren't good enough to get a proper fit. So let's have a look at each category of galaxy. First one, the magenta galaxy are the oldest galaxy. A good example would be the BCG. And here, indeed, I'm showing you the BCG, its SED, and its age and characteristic time distribution. What you will notice is that the age is around 2 gigayears, but it's poorly constrained. Can't really be helped. There is a lot more difference between, say, 1.5 and 3 gigayears and between 10 and 12, but there isn't still that much of a difference. Hence the poor constraint. What we can see is that it's still very old because the universe was 3.35 gigayears old at this redshift, so 2 gigayears start to be quite old. You can notice also that the characteristic time is quite short. It's about 300 million years old. We have another set of old galaxies, the orange one, but they are just young enough that we can get a better grasp on the age. They are aged about 1 to 1.5 gigayears, and the characteristic time is again quite short. It's interesting to note that the most massive member in XLSSC 122 are either into the orange or in the magenta category. So they are old quench galaxy. We have a transitive category with age of 0.5 gigayears, and again, quite a short characteristic time. In fact, we have only 4 members in that category, and they are markedly less massive than the member into the orange and magenta category. Last but not least, the star-forming members. They are very young, and indeed they have a very poorly constrained characteristic time, which is to be expected with such young an age. However, you must be careful in overinterpreting this age because the blue massive stars are so bright that they can hide an older population. And I made some tests with mud photometry and found that around or above 20% of young stars, it's very difficult to know if you have an underlying older population or not. So we can say that these members are forming stars, but that's about all that we can say. That and that they are less massive than some of the quench galaxy. We have also one galaxy that doesn't fit into any category, and it's an interesting one, but unfortunately we have only poor constraint on its parameter because it's very dusty. So I just wanted to mention it because it's interesting. What we have so far is we have a red sequence with age varying from 0.5 to 3 gigayears, although the most massive galaxies tend to be slightly older with age above 1 gigayears. There is only 4 members which are 0.5 gigayears approximately, and together with the short time formations time scale that we see for all the quench members, this seems to hint at a rapid quenching mechanism. Another thing we can do is we can make a link with the cluster assembly. Now, we cannot go back in time and try to measure the assembly of XLSSC122 over the redshift. So what we do is we use simulation. I must thank Doug. We basically dug into MultiDark Planck 2 simulation for 500 clusters similar to XLSSC122 in mass, and organized them in such a way that I could do these histogram. Here I'm showing you the evolution of the cluster by chunk of 20% of assembly. And I divided the histogram in two because there is a lot of overlap. So here it's from like 10, in the left it's from 10 to 90%, and in the right it's 30 and 70%. Very good. But it's very interesting only if we try to make a link with the star formation history. And here I'm making the exercise with the BCG. What you can see is the BCG has probably formed before the cluster at 10% of its mass. And it might even have formed before the cluster had accreted 10%. Of course, you should do a similar exercise with the older magenta members, and with the other category as well. So here I'm giving you some example. And this way you can draw a cluster timeline, trying to assess when the star formation happened relative to the cluster assembly. So this is a work in progress. In summary, XLSSC122 members exhibit a variety of age, and the evolving members all have short star formation history, which seems to hint at a rapid quenching. And the oldest galaxy form with the cluster at 30% or less of its mass, and some of them might even have formed with the cluster at less than 10% of its mass. And my take-home message would be that if you if you really want to understand what's going on into your cluster, you need to have multi-wavelength data. So thank you, and I'm going to take questions.